Hi students, today in class we will be learning about glaciers. This lecture goes along with your Unit 3 homework for assignment. You should have completed the first half with the lecture about deserts, and then now the second half will pertain to today's lecture about glaciers. To begin, let's start by looking at this image on the screen. If you look closely, when you look at this image, what you might first think that you're looking at is actually a mineral. But what we're looking at here is glacial ice. This image is a thin section, and what we see is we're seeing that ice is actually made up of a mass of crystalline grains. And so the reason that glacial ice resembles a mineral is because ice, in fact, actually is a mineral. It meets all of our requirements as a mineral, where it is naturally occurring. It is an inorganic solid. It has a defined chemical composition and a defined chemical structure as well. So the reason when we look at this image of glacial ice in thin sections that it looks like crystalline grains that we might see in a rock is because what we're seeing in that rock are different mineral grains, and ice is in fact a mineral. But this gives us an idea of what we're talking about as we start to dive into glaciers and the glacial ice they contain. Now that we have a sense of what glacial ice looks like, at least in thin section, let's go ahead and dive in and investigate the different types of glaciers that exist on Earth. Before we investigate the different types of glaciers, it's important that we first define what a glacier is in scientific terms. A glacier is a large mass of ice on land that moves under the force of gravity. And so what this tells us is that in order for something to be a glacier, not only does it have to be a large accumulation of ice, it has to be large enough that it's moving due to gravity. So basically its weight is great enough for it to move downhill with the aid of gravity. So now that we have a definition of what a glacier is, let's go ahead and look at our two major types of glaciers. Those are valley glaciers and continental glaciers. The first type of glacier I have up on the screen is known as a valley glacier. It might not be a surprise that a valley glacier is of course located in a valley. A valley glacier is a river of ice that forms at high elevations where snow accumulates, and that accumulation of snow over time will lead to the formation of glacial ice, and there's been so much snow and glacial ice that's formed that it starts to move under its own weight. If we take a look at the image on the screen, this image really helps convey this idea of a valley glacier being a river of ice. We can see this is located in the mountains where we have this extensive ice that is moving downhill under its own weight. Valley glaciers can be found in mountain ranges, and so these are mountain ranges that can be entirely landlocked, but what we'll also find is sometimes these valley glaciers can extend from the mountains all the way down to the ocean. If valley glaciers do extend all the way to the ocean, the edge of the valley glacier is exposed to the water, which has a very strong, of course, temperature differential, the water versus the ice. So if there is a valley glacier that reaches all the way to the ocean's edge, what can happen is the end of the valley glacier can break off through a process known as iceberg calving. We can see this idea of iceberg calving in the image that just appeared on the screen. So with valley glaciers, they are going to originate high up in the mountains, and if it's in an environment, it can move all the way down to the ocean, and then some of that ice is then returned to the ocean through iceberg calving. The second type of glacier that we'll learn about today is something known as a continental glacier. A continental glacier is a thick, slow-moving sheet of ice that covers a large portion of the continent. We have two continental glaciers that exist on Earth today. There is a continental glacier that covers Greenland, and so we can see an aerial photograph of Greenland giving us a sense of this continental glacier in the image on the left-hand side of the screen. And the second location that there's a continental glacier is Antarctica. We can see a Google Map image of Antarctica on the right-hand side of the screen. In both of these cases, notice that these are areas that are covered with ice and snow with this continental glacier. Continental glaciers only cover about 10% of Earth's surface, but they contain enormous reserves of fresh water. So they contain approximately or about 75% of the world's fresh water. Let's go ahead and take a closer look at both the Greenland ice sheet and the Antarctic ice sheet. Let's start with the Greenland ice sheet, which I have up on the screen. The Greenland ice sheet is an ice sheet that covers a very extensive portion of Greenland. Greenland is covered by approximately 2.6 million cubic kilometers of ice, which covers about 80% of Greenland. We can get a sense of this ice coverage by looking at the map that's on the left-hand side of the screen. The map reveals elevation above sea level. So starting at sea level, which is represented with green, and this is 0 meters, going all the way up to over 3,000 meters, which is represented by the yellow color. This gives us a sense that we have up to or a little bit more than 3,000 meters of ice at the center of Greenland. And in fact, in the middle of the island, at the center of this continental ice sheet, the ice is 3,200 meters thick. This is a lot of ice that covers an enormous portion of the continent. We can get a sense of this cross-section view of how extensive this ice is by looking at the image below the map on the left-hand side of the screen. This shows us that there is an ice cap that reaches the highest elevations in the center. What you might also notice here is that the ground beneath the ice cap has begun to subside or sink. And the reason this happens is because of the weight of the ice. By adding ice over the land surface, the ice is going to provide overriding pressure, which is going to cause the lithosphere below to subside or to sink. So you can see that there is subsidence of the crust below central Greenland due to the presence of this ice sheet. When this continental glacier reaches the ocean, what happens is it tends to kind of peel off into things that resemble more like valley glaciers. So it starts to form kind of narrow tongues. And when these rivers of ice reach the ocean, what can happen is that ice can be lost through that calving process that we talked about earlier when we talked about valley glaciers. So this is a Greenland ice sheet, which has over 2.6 million cubic kilometers of ice coverage that covers 80% of the Greenland landmass. Now that we have a sense of the Greenland ice sheet, let's go ahead and take a look at the second continental ice sheet, which is the Antarctic ice sheet. Antarctica, of course, is located over the South Pole. Antarctica is a larger continent than Greenland, and so there is significantly more ice that exists on Antarctica as well. About 13.6 million cubic kilometers of ice cover Antarctica, and over 90% of Antarctica is covered with this ice. We can take a look at the map on the right-hand side of the screen to understand a little bit more about the geography of Antarctica and this ice coverage. What you'll notice with Antarctica, it's divided into 3 sections. There is East Antarctica to the east. This is the largest landmass. And then there's West Antarctica to the west of East Antarctica. And then if you look a little bit northwestward of West Antarctica, this is known as the Antarctic Peninsula. The thickest ice, the thickest continental glacier aspect is found in East Antarctica. And so if we look closely at this map, we'll notice that the elevation in the center of East Antarctica is greater than 4,000 meters. So this tells us that the ice thickness in East Antarctica is up to 4,000 meters in thickness, meaning that this is a lot of ice that is very thick located over East Antarctica. East Antarctica is connected to West Antarctica by something that is known as the Ross Ice Shelf, which we can see in the kind of middle section of the map here. The Ross Ice Shelf is a thick layer of ice that's about the size of Texas, and it floats on the Ross Sea. So this is sea ice rather than a continental glacier because it's covering the ocean and not covering the land. But this Ross Ice Shelf is going to provide one connection we see between East Antarctica and West Antarctica. To get a sense of the dynamics of this continental glacier, we can take a look at the cross section that is highlighted on the map and shown below the map on the right-hand side of the screen. The cross section goes from A to N, with A being just a little bit to the south of the Antarctic Peninsula. Notice that the A to M section goes across the West Antarctic ice sheet, then across the Ross Ice Shelf to the East Antarctic ice sheet. This is a great way to see that the largest portion or the thickest portion of ice is located over East Antarctica, and West Antarctica still has a very significant amount of ice, but we don't see that it's quite as thick as over East Antarctica. In both incidences, we also see that because of this overriding pressure provided by the glacier, that there is subsidence of the land surface below both the East Antarctic ice shelf and the West Antarctic ice shelf. Now that we have an understanding of what a glacier is and our two different types of glaciers, a valley glacier and a continental glacier, let's go ahead and start to investigate where glaciers form. So because glaciers are large amounts of ice, they can only form in certain locations on Earth. So to better understand this, let's go ahead and take a look at some of the requirements that are needed for glaciers to form. So the first requirement for a glacier to form is that temperatures must be cold enough for snow to remain on the ground year-round. If we think about this in a global perspective, there are not many locations on Earth where snow can remain on the ground year-round. There's really just two subsets of locations where this can occur. If we take a look at the image on the left-hand side, this is giving us an indication of one such location, where this location, of course, would be located at high latitudes. And so we've learned previously in this unit that with the climate system, heat is gained at the low latitudes and tropics, and heat is lost at the mid and high latitudes. So at the high latitudes, these are the only locations where we see that ice remains on the ground year-round and close to sea level as well. So one requirement is that it has to be in a place where temperatures are cool enough. So that would be our high latitudes. So that's the Arctic and then the Antarctic. And so that's why we, of course, see continental glaciers that exist on Greenland, the continental landmass of Greenland, and then also the continental landmass of Antarctica. The second type of location that exists that potentially has that option of having snow remain on the ground year-round would be located at high elevations. So if we take a look at the image on the right-hand side of the screen, this is an image, I believe it's taken, a photograph that's taken from Alaska. And in the mountains of Alaska that are at a high enough elevation, their temperatures are cold enough for snow to remain all year. So this would be another location in which we could see this requirement met. We could see it met in terms of our high latitudes with Greenland and Antarctica, and then we can also see this requirement met if we're at high elevations or high altitudes in mountain ranges. The second requirement that is needed for glaciers to form is that there must be abundant moisture in the air that leads to precipitation. So this also indicates that in order for glaciers to form, they need to be in regions where there is enough moisture in the air for precipitation to form. So what you'll notice below our second requirement, I've included a figure that is giving us a sense of the movement of the wind over a mountain range. So what we can see here is if we have strong winds that move off of the ocean, that means that these winds are going to be carrying a large amount of water vapor that they picked up over the ocean environment. Those winds through orographic uplifting are lifted up over the mountain ranges. And as the air mass is lifted up over the mountain range, what happens is the air cools due to the environmental lapse rate in the troposphere of 6.5 degrees Celsius per kilometer. As it cools, the water vapor will get to its saturation point, it will condense, and precipitation will occur. So we do find that there is enough precipitation, especially in these environments where we have mountains that are located next to an ocean, and then looking on that windward side, there's the potential to form glaciers there. So if we think about this in the context even of thinking about Antarctica or thinking about Greenland, both of these are coastal environments where that moisture is picked up off of the ocean and then transported onto the land, and that's helped fueling some of the precipitation that's needed in order to generate snow and eventually glacial ice. Now that we have a sense of where glaciers form and the requirements involved in forming a glacier, let's go ahead and take a look at specifically how a glacier forms. So we know that glaciers form in regions where there are cold temperatures, and those temperatures are cold enough for snow to remain on the ground year-round, and there is abundant moisture that can lead to precipitation and ultimately the formation of snow. So the first step that we have to have in terms of forming a glacier is we have to have enough snow. So if we take a look at the screen, this gives us an indication of if the temperatures are cold enough and we have enough moisture in the air, snow can be produced. So if we look at the figure on the screen, what you'll notice is, first of all, you'll see a skier skiing some powder there, that powdery snow. And the reason that snow can be more powdery is because it contains a lot of air. So when snow falls on the ground, what is actually there? It's about 10% snow, or 10% is precipitation, and 90% air. So there's a lot of air that exists within this snow. But this is the first step where we have to have precipitation in the form of snow. And let's go ahead and take a look at what happens to that snow over time. Over time, as more snow falls, that's going to create some overriding pressure. And that pressure will ultimately influence the snow below it, and it will generate the formation of granular ice. What happens here is that additional snow, it creates this overriding pressure that's going to compress the snow that was originally there. And as that snow is compressed, what we can see is we're reducing the amount of air or the amount of pore space that's present in that snow. So we're reducing from about 90% air to 50% air. And in doing so, this is also actually modifying the ice crystals themselves, where we can see that they're no longer these kind of large, intricate snowflakes, but instead they have become kind of reformed and remelted to form granular ice. If you are a skier, you might know that skiing on kind of powdery snow is excellent, but if you're skiing on granular ice, that is much less pleasant. After the formation of granular ice, as that snow continues to accumulate above the granular ice, this will generate even more overriding pressure and will cause greater compression of the granular ice. What we can see is that granular ice will continue to compress to a point in which there is not 50% air, but rather it compresses to about 20 to 30% air, and you get a change in the dynamics of those ice crystals themselves as well. At this point, this creates another component, which is referred to as firn. We can see a great example of firn in the image on the left-hand side of the screen on that lower image. This is really giving us the sense of we're looking at this cross-section. The upper layers are snow going into granular ice and then eventually into firn. The idea with firn here is that we have significantly less air between these pore spaces. So with snow, we have 90%, with granular ice, we have 50%, and then with firn, we have 20 to 30%. As this continues to be compressed and we get to a point where there's less than 20% air bubbles, this is when you actually form what's referred to as glacial ice. In glacial ice, we do have the ice that recrystallizes, and we can see that these ice crystals are getting progressively smaller as we move from snow to granular ice to firn to glacial ice. So with the formation of this glacial ice and all of these steps of first forming snow, then granular ice, then firn, and then this glacial ice, this is a great example of how glaciers grow. And the way that glaciers grow is through this process of accumulation, where more snow is accumulated, and over time, that accumulation is going to lead to a growth of a glacier. Once the glacial ice is compressed to less than 20% air bubbles, and it is heavy enough to move under its own weight with the force of gravity, that's when it actually becomes a glacier. We just learned that glaciers grow through this process of accumulation, where snow is accumulated, and over time, that snow is going to be compressed to form granular ice, and then firn, and then glacial ice. But there's another important component that we need to factor in how glaciers change. Once a glacier forms, it can continue to grow through this process of accumulation. And so if we look at the figure on the screen, what we'll notice here is that accumulation is going to occur in the upper regions of the glacier, where snowfall is dominant and the snow will start to turn into ice. So we can see this accumulation dominant zone near the mountains in the upper portion of the glacier. However, in addition to glaciers growing, what will also happen is ice is lost as well. And the way that some of this glacial ice is lost is through a process that's known as ablation. Ablation is the total amount of ice that a glacier loses annually. So we have a few different ways in which ablation can occur. Ablation can occur purely as melting, so this is just melting the ice to form liquid water. It can also occur through the process of sublimation, and that's where the ice actually, instead of going ice to liquid to a gas, just goes straight from ice, which is a solid, to a gas. Wind can also promote melting as well, and we can also have iceberg calving that happens when these continental glaciers or these valley glaciers are going to reach the ocean. So all of these are components of ablation, which means ultimately this idea of how much material is lost from a glacier in a year. So what's important here, to better understand the dynamics of glaciers, we need to understand how accumulation and ablation are going to balance each other out. So this is referred to something known as a glacial budget. If a glacier stays exactly the same size, what this means is accumulation is equal to ablation. So all the new snow and ice that accumulates, the equivalent will be lost. And so as a result, the glacier stays in a steady state. It doesn't grow, it doesn't shrink. I should highlight here, we already learned that accumulation occurs in the upper portion of the glacier, and in the bottom portion, the second half of the glacier, that's at lower elevations, this is going to be where we're going to see ablation is dominant. So if the glacier remains the same size, the accumulation must equal the ablation. In most cases, we do see that glaciers are going to have some type of movement. They'll either grow or they'll retreat. And so in order for a glacier to grow, accumulation has to be greater than the amount of ablation that occurs in a given year. And if a glacier retreats, we see the opposite, where accumulation is less than ablation. Let's go ahead and take a look at how glaciers are changing around the world today. Let's take a look at one example here, but there are many different examples that we could focus on. The example we see here is Coricalis Glacier, which is located in Peru in the Andes. What you'll notice on the left-hand side of the screen, this is a photograph or an image from July of 1978, and on the right-hand side of the screen, this is an image just from July of 2004, so this is still 20 years ago. Take a moment and think about how has this glacier changed. What you're hopefully noticing here is that the glacier in July of 1978 was much larger and much more extensive and overall bigger than the glacier of July 2004. So what this indicates overall is that this glacier is retreating. And so in terms of glacial budgets, this means that ablation would be greater than accumulation, leading to the retreat of this glacier. Unfortunately, This is a trend that we see happening around the world. So this doesn't only happen in Peru, but this is happening around the world where we see that glaciers overall are retreating. And the reason they're retreating is because our climate is changing. As temperatures warm, it means that the temperatures are not cold enough to support additional accumulation, and they increase the amount of ablation, which is resulting in the retreat of glaciers worldwide. Next, let's take a look at how glaciers move. So we studied this idea or investigated this idea when we talked about stream transport last week. But with stream transport, we learned that we have flow in streams that's either laminar flow or turbulent flow. So turbulent flow dominates stream environments, but the other one, the opposite, laminar flow, is actually what dominates the movement of glaciers. So laminar flow is also thought of as kind of plastic flow. And laminar flow is going to occur when we see the entire mass moving at a relatively constant velocity and speed. So to get this idea of laminar flow, we can take a look at the thin section on the upper side of the upper portion of the screen. And what you'll notice here is we have a series of ice crystals. And as they're starting to move, the individual ice crystals start to stretch and rotate a little bit, but they're all generally moving in that same direction. With laminar flow, this is the typical way that glaciers move, this more kind of constant, steady motion. And this has to do, of course, with the fact that gravity is an acting force and that the glacier is moving as a result of its mass and the force of gravity. With this laminar flow, it is generally consistent, but what we do find is that the laminar flow has greatest velocities at the surface of the glacier, and then as you move from the surface of the glacier down through the ice towards the bedrock, the velocity is actually going to decrease. And if we think about this logically, it makes sense because the ice that is right along Earth's surface is going to have a greater amount of friction, and that friction is going to result in a little bit of a reduction of velocity. So with this laminar plastic flow, we see that the overall direction of movement is the same. This is going to kind of stretch and rotate the ice crystals, and it's going to cause the movement of this glacier downhill. So under the force of gravity and its own weight, we'll see that the fastest velocities are towards the surface of the glacier, where we have the top of the glacier exposed to the atmosphere, and then we'll see the velocity decrease as you go down towards the bedrock or the lithosphere, as we have that interaction between the ice and the lithosphere, which ultimately is going to cause some friction and cause it to slow down. We see that this process of laminar flow in glaciers happens when these glaciers are found in very cold climates. There is a second method in which glaciers can move, and this second method is known as basal slip. Basal slip happens when a glacier is sliding along the boundary between ice and the ground. As the glacier slides along this boundary, what tends to happen is that the melting point of ice decreases due to the overlying pressure of the ice, and there is a very thin layer of water that exists between the glacial ice and the ground surface or the bedrock. This creates an area in which slip can occur. This occurs very much in the same way as an ice skate. If you've ever gone ice skating or played hockey, ice skates have a blade that provides pressure between your foot and the skate and the ice itself. That pressure melts the ice, and this is what allows you to skate on the ice or slide or slip on the ice. So this works with a glacier as well, where this overriding pressure by the glacier melts a little small layer of ice, and as a result, occasionally the glacier can move really quickly in kind of an abrupt surge forward on this melted ice, on this melted layer. So when it slips forward very quickly and moves a farther distance, this is known as basal slip. So when we think about the movement of a glacier, it's actually both components here, where the overall movement is the laminar flow, but then you will have occasional times where basal slip is going to dominate and you'll have more of a surge forward with this glacier. In valley glaciers will move by both of these components of laminar flow and basal slip. So first, let's take a look at this valley glacier I have on the screen, and let's investigate the components of laminar flow. With laminar flow, the flow is fastest in the middle of the glacier, and this is because this is the part that is going to be least restricted by any type of topography or obstacles. We already discussed how the velocity of laminar flow decreases as you go from the top of the glacier to the base of the glacier, and that's due to the friction between the ice and the bedrock. And so we know it's fastest in the middle at the top of the glacier, and then it would be slower at the base. This same principle also applies when we move towards the sides of the glacier as well, where we find that the velocity of laminar flow is slower at the sides of the glacier, and this is because that ice is going to be interacting with the bedrock. Think of this as kind of the walls that are containing the glacier, and so the ice interacts with the bedrock again on the sides, and this is ultimately going to generate more friction, which impacts the velocity of our laminar flow. So in addition to the laminar flow, with the highest velocities in the middle and the surface of the glacier, and the lower velocities at the base and the sides of the glacier, we also have basal slip that would contribute to more kind of surges forward in the movement of these valley glaciers. With the friction that is generated between the ice and the valley walls, this friction can ultimately lead to the formation of some interesting but very deadly features that we see associated with these glacial environments. Because of that interaction between the valley walls and the movement of the glacier, we can see that the formation of crevasses occur. Crevasses form when ice drags against valley walls as it curves, or due to irregularities in the valley floor. So this ultimately disrupts the laminar flow, and as a result leads to the formation of these crevasses. Crevasses are breaks in the ice that can descend very great distances. So if you ever are traveling on a glacier, one thing you have to be really careful of is a crevasse, because crevasses can almost appear out of nowhere, and then they really they fall to great depths. You can see an image of me in Norway on a glacier, just traversing across this glacier in Fogelfana National Park, where you'll notice you want to make sure you do this with the correct gear and the correct knowledge when you do go across glaciers. We can see many crevasses kind of transversing a crevasse field in that image. So crevasses are features that form as a result of this frictional drag of the ice compared to the valley walls, or irregularities in the valley floor. Valley glaciers move by a combination of laminar flow and basal slip, which is a little bit different than we see with the movement of continental ice sheets. With continental ice sheets, these tend to primarily move under laminar flow. With the continental ice sheets, they are thickest in the center of the continent, and that's also where they're fastest as well. So they're fastest at the surface, and the velocity slows down towards the sides. But overall, with continental ice sheets, we see that the majority of the movement is driven primarily by laminar flow. Now that we've learned the fundamentals about glaciers, let's go ahead and explore glacial landscapes. Glaciers erode, transport, and deposit rocks on sediments, leaving distinctive features behind that indicate that the area was transformed by glaciers in the past. Let's go ahead and investigate some of these features that develop in glacial landscapes. The first feature that I want to introduce is something that's known as glacial striations. We actually took a look at glacial striations early on in the semester when we explored the hypothesis of continental drift. Striations are abrasions that exist on the bedrock from rocks being dragged along the base of a glacier. We can see how this works by looking at the figure on the left-hand side of the screen. As the glacial ice moves, what happens is it picks up rocks and small boulders and starts to move those rocks and small boulders along the bedrock with the ice. As this happens, if there's some type of kind of irregularity in the surface, these rocks can scrape or abrade the bedrock beneath them, leaving behind a feature that resembles a line, which is referred to as a striation. So we can see the active formation of striations in the figure on the left-hand side of the screen, and then on the right-hand side of the screen, we can see the striations that are left behind on bedrock after a glacier recedes. So in this case, in this image, we see that there's no glacier present, but the way that we know that a glacier did transform and erode this landscape in the past is due to the presence of these glacial striations. These striations can also help geologists determine the direction that the glacier flowed. Now that we've investigated glacial striations and have learned that glacial striations are a result of erosion and transport of rocks and other debris along the base of a glacier and that interaction between the base of the glacier and the bedrock, let's go ahead and take a look at other erosional features that are characteristic of glaciated environments. If we take a look at the image on the screen, the upper image, this gives us a great example of features that form when we do have a glaciated environment. What we'll see here is we have one main valley glacier that we see kind of in the lower part of this image. This main valley glacier has started to carve out a valley, and notice that this valley has a very distinctive U shape. So if you're in a region where you see a U-shaped valley is a great indication that this area in the past was once glaciated. So this is different than the type of valley that we expect if an area was eroded by a stream. If we look at the lower image on the screen, this gives us an idea of the type of features we expect with stream erosion. So if we have a stream that's eroding an area, this will generate a V-shaped valley. So a V-shaped valley is going to have much steeper walls, much steeper valley walls that form more of a V shape than the U shape that we see indicated here. So a U-shaped valley is indicative of glacial erosion, while a V-shaped valley is indicative of stream erosion. The main valley glacier will form this very distinctive U-shaped valley that we just took a look at, but some of these smaller tributary glaciers that feed into the main valley glacier can form some other interesting landscapes that are key indicators that these areas were glacially eroded in the past. Let's go ahead and take a look at these additional features that we might see at slightly higher elevations. The first feature I want to introduce is a feature that's referred to as a cirque. We can see a photograph of a cirque that just appeared on the right-hand side of the screen. The cirque is at the head of a glacial valley, and it has nearly vertical upper walls that are flat and kind of have a more hollowed out base. So if you have ever gone up to Snow Basin and gone up to Needles Lodge, in the summer, you can hike up the Cirque Trail, which takes you to the top of Needles, and that's a great classic example of a cirque, where you have more of a hollowed out base, and then you have kind of steeper walls as you go up to the top of the cirque. If you have multiple of these smaller tributary glaciers that are moving downslope from a higher, more elevated point, they can ultimately form the feature that's known as a horn. So this means that you have kind of glaciers moving down multiple sides here, multiple tributary glaciers, that's leaving this very prominent feature behind, which is referred to as a horn. One of the classics you might think of is the Matterhorn, and this is a great indication that this area was eroded by glaciers in the past. In addition to cirques and horns, an additional feature that we see represented in glaciated landscapes are arêtes. Arêtes are sharp, jagged crests that are located along an eroded divide. And so this would be kind of the edge, the valley edge of one of these tributary glaciers, which we can see in the photograph and the figure on the screen. The final feature that I want to highlight again is this area where we would have that main valley glacier going through. This would ultimately form a U-shaped valley. So we can see the U-shaped valley in the figure on the left side of the screen, and then we can see a photograph of a U-shaped valley that's filled with water on the right-hand side of the screen in that lower image. When we do have a U-shaped valley that's filled with seawater, so water from the ocean, this forms a very distinctive feature that's known as a fjord. And so fjords are common in Norway and New Zealand, and many other locations as well. You can find them in Patagonia, and these fjords give us the indication that these landscapes were eroded and carved by glaciers. When we do have a U-shaped valley, these U-shaped valleys do create very steep walls. And so as a result, you can have something that's referred to as a hanging valley, and that's usually represented by some type of waterfall that comes directly off of the valley walls. So we can see a few examples of hanging waterfalls in the figure on the screen, and then we can also get a sense of kind of this U-shaped valley when we look at the photograph that's on the lower left-hand right side of the screen of Yosemite Valley. This is kind of a classic glacially eroded landscape, and then there are also many hanging waterfalls in this area along the valley walls as well. Now that we understand some features that can be associated with erosional aspects of glaciers, let's go ahead and take a look at more depositional features that are related to glacial landforms. If we take a look at the image on the side of the screen, on the left side of the screen, we can see a typical valley glacier. What you might notice is surrounding the valley glacier, on the edges, and then also through the middle and at the end of the valley glacier, there are large deposits of sediments. These deposits are referred to as moraines, and moraines are also a great indicator that a glacier was present in the past. So as we saw from those erosional features, glaciers are able to erode and also weather significant amounts of material. They can then transport that material and eventually deposit that material, and that's what we're seeing in terms of the formation of these depositional moraines. So if a moraine exists on the edge of a glacier, it's referred to as a lateral moraine. If a moraine exists in the middle of a glacier, this is a medial moraine. And if it is found at the end of a glacier, this is referred to as an end moraine, or a terminal moraine, and it indicates the greatest size that this glacier ultimately was, and then gives an indication of how it's been retreating and depositing material. The material that's deposited in a moraine is referred to as glacial till, or sometimes just as till. Till is unstratified and poorly sorted sediment that's deposited by this melting ice as a glacier retreats. We can take a look at the image on the screen to get a better sense of what glacial till looks like. When we look at this image, what I want you to notice is that glacial till is going to be very poorly sorted. And this means that we have a wide variety of sediment sizes. There's everything from very small fine-grained sands and clays and silts to large boulders. And this is because glaciers have this amazing erosive power. So they can move very large materials, very large grain sizes like boulders and cobbles, but then of course they also move finer grain sizes as well, but they deposit it in these large, unstratified and poorly sorted deposits known as till. If you do have a very large boulder that is moved by a glacier, this is called an erratic or a glacial erratic, and this is also a depositional feature that is quite indicative of glaciers being present in the area and glacial landforms. Now that we have a good sense of what moraines are and glacial till, let's go ahead and take a look at a few additional features that can form from the deposition of glacial sediment. This next feature is the one that I have up on the screen, which is referred to as a drumlin. We can actually see multiple drumlins in this image. A drumlin is a large hill of till and bedrock that form parallel to the direction of ice movement. So we can see that these drumlins extend from the edge of the glacier, which is a different direction than a end or terminal moraine. These are going to be parallel to the movement, and what happens in this case is sediment at the base of the glacier is trapped by some type of irregularity in the surface, which is ultimately generating the deposition of sediment in this large hill that's located in a more parallel direction to ice movement. The next feature that I want to introduce that is formed as a result of a glacier is something that is known as an esker. We can see an example of an esker, or two examples of eskers, in the image on the screen in this environment that is clearly not glaciated anymore. But these eskers are evidence that this area was once shaped and eroded by glaciers. Eskers are long, narrow, winding ridges of well-sorted sand or gravel. So this is different than the drumlins, where the drumlins and in general glacial till is very poorly sorted, where we can have fine grains and larger grain material and cobbles. With these eskers, they are much more well sorted and only composed of sand or gravel. And the reason for this is they form in a slightly different way. They form as a result of meltwater streams that flow in tunnels at the bottom of a glacier. So the meltwater streams that are going to move meltwater away from this glacier. And so that's why we see that they're more well sorted, because they are being transported by the water that is associated, the meltwater associated with the glacier, rather than just being transported by the ice. These long, narrow, winding ridges of well-sorted sand and gravel, they're found in the middle of ground moraines. So this is usually a component of moraines. The final feature that I want us to investigate in a glaciated landscape, or a once glaciated landscape, is something referred to as a kettle or a kettle lake. A kettle is an undrained depression that has steep sides and it can contain water. So we see a great example on the screen. There are actually many different kettles in this image where they look like very small lakes here. The way that kettles form is they form when an isolated block of ice has detached from the glacier in the outwash plain, and then that isolated block of ice melts, and as it melts, it's going to create a depression and fill that depression with water, forming a kettle or a kettle lake that we see here. The final aspect that I want to introduce here is not exactly a glacier, but it is a feature that's very important, and it's found in very cold environments, in similar environments that we find glaciers in, especially at our higher latitudes. This last thing I want to introduce is something that's referred to as permafrost. So we can see a pretty dramatic version of permafrost in the image on the screen. Permafrost is located at our high latitudes, especially in the northern hemisphere, and we can see this highlighted on the map in the upper left-hand side, where there's significant permafrost in Greenland and the Arctic and northern Canada, and then kind of going into southern Canada and Europe and Scandinavia as well. So permafrost it's not a glacier. It's frozen soil and aggregates of ice crystals. In order for something to be considered permafrost, so for soil to be considered permafrost, the soil must remain below 0 degrees Celsius, so below freezing, for at least 2 years. Permafrost covers over 25% of the Earth's surface, so it actually covers a significant portion of the Earth's surface. And in locations like Alaska and northern Canada, it can be as much as 300 to 500 meters thick. Permafrost is becoming incredibly important as we understand how our climate changes, because as the climate warms, the permafrost is melting. Permafrost itself contains significant amounts. It serves as a significant sink for carbon dioxide and methane. So as the permafrost melts, what happens is the carbon dioxide and the methane are then released to the atmosphere, which is going to continue to enhance the greenhouse effect. So permafrost is something that is really important in terms of the balance in our climate system. It's something that serves as a carbon sink for carbon dioxide and methane, but as the Earth's temperatures continue to warm, we find that this permafrost is melting, and as it melts, it's going to release that carbon dioxide and methane to the atmosphere, which is going to continue to enhance the greenhouse effect. It's going to serve as a positive feedback to enhance the greenhouse effect and make temperatures warmer. So this is something we definitely want to keep our eye on and be aware of as our climate changes, of how the extent of permafrost is also fluctuating as well. So this will wrap up our investigation into glaciers. So please make sure that you complete your homework assignment, which is Unit 3, Homework 4, which is about both deserts, which was our first lecture for the week, and glaciers, which is our second lecture for the week, and make sure you submit this on Canvas. In addition, please also take your quiz, which will be a great way to reinforce some of these concepts and assess where you are with this material and this content. Please don't hesitate to reach out to me by email if you have any questions.